Welcome. Today we are diving into one of the most fascinating and challenging problems in modern mathematics, the Birch and Swinnerton-Dyer conjecture. This conjecture sits at the crossroads of elliptic curves and L functions, connecting the worlds of geometry and analysis in a profound way. It is also one of the Clay Institute's Millennium Prize Problems. Solving it will win you $1 million. So, what exactly is an elliptic curve? An elliptic curve is essentially a non-singular cubic curve in two variables defined over a field, and it has a special point at infinity. Non-singular means that the curve has no cusps or self-intersections. Typically, we represent an elliptic curve using the Weierstrass normal form, which is given by the equation y squared equals x cubed plus a times x plus b. Here, a and b are constants that determine the specific shape and properties of the curve. Now let's talk about L functions. L functions are meromorphic functions on the complex plane that generalize the famous Riemann zeta function. They are defined by a Dirichlet series, expressed as L of s equals the sum of a sub n times n to the power of negative s, where s is a complex variable, n ranges over the natural numbers, and the a sub n are coefficients that encode arithmetic information. L functions also possess some very useful properties. They have an Euler product formula, allow for analytic continuation, and satisfy a functional equation. Here comes the main topic. The Birch and Swinnerton-Dyer conjecture, often abbreviated as the BSD conjecture, proposes a deep connection between an elliptic curve and its associated L function. The conjecture states that the algebraic rank of an elliptic curve is equal to the analytic rank of its L function. In mathematical terms, rank of E over Q equals the order of 0 at S equals 1 of L of ES. This equation tells us that the number of rational points on an elliptic curve is intimately connected to the behavior of its L function at S equals 1. The BSD conjecture is significant because it bridges the gap between the discrete world of arithmetic, represented by the group of rational points on an elliptic curve, and the continuous world of analysis, represented by the behavior of the L function. Geometrically, it connects the finite group of rational points to infinite analytic properties. Analytically, it transforms difficult geometric questions into tractable analysis. The implications of the BSD conjecture extend far beyond pure mathematics. Elliptic curves, and therefore the BSD conjecture, have significant applications in cryptography. Understanding elliptic curves is fundamental to modern encryption and digital security. Also, it helps in solving Diophantine equations and understanding rational point distributions, all of which have wide-ranging consequences. So, where do we stand with the BSD conjecture today? Significant progress has been made, and the conjecture has been proven for special cases, such as elliptic curves with complex multiplication. However, the general proof remains elusive. Connecting the finite and infinite worlds continues to be a significant challenge for mathematicians. In conclusion, the Birch and Swinnerton-Dyer conjecture represents the deepest mystery connecting geometry and analysis in modern mathematics. Solving it would revolutionize our understanding of elliptic curves and unlock new frontiers in number theory. It remains one of the 7 Millennium Prize Problems. If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content.